in chapter 11, we're going to look at atomic theory and the quantum model of the atom. So if you've taken physics, you may have seen a lot of this stuff before. If not, no big deal. The book kind of goes more in depth than I really want us to go for this particular chapter. So if you're reading the book and you're like, oh my gosh, that's so much more, that's way more than we need to know. We're just going to really skim the surface of this particular topic. So electromagnetic radiation. So you may have heard of that before. Electromagnetic radiation. It basically includes it's a form of energy that occurs as waves. And so you're looking at like radio waves and gamma rays, X-rays, UV, IR. All these sorts of things are part of the electromagnetic spectrum. This is all part of the electromagnetic spectrum. You don't have to memorize this. We're gonna do a whole lab called the flame test, where we're looking at the visible spectrum. So we're going to we'll talk a lot about this. So we get to see pretty colors. We're going to burn things, and it's going to be a lot of fun. So we'll refer back to this visible spectrum later on when we look at different colors. This is the part that your eye can see. We'll talk a little bit about UV light as well in that lab. So all light, all of this, all these waves are traveling at the speed of light. This is 3 times 10 to the 8 meters per second. That's a constant. We're not going to do any calculations in this chapter, I don't think. So if we did, I would give you that, but I don't think we need this right now. Electromagnetic radiation. So, sorry, electromagnetic waves. More Greek letters in case you didn't get enough. We have wavelength, which you may remember from, I don't know, some math class. You're measuring from like the peak of one wave to the peak of the other, or the trough to the trough. Either way is fine. But it's kind of the distance between these two waves. That's the wavelength, and that's symbolized by lambda. And nu is the frequency, which is basically telling you, how many times do I pass a certain point in a given amount of time. So frequency, like how many times is this wave going to hit this post in, per second or whatever. They're very much related. Wavelength, so what's nu? That's my nu, that's my frequency, is c over lambda. C again is the speed of light. So what's nu? C over lambda. So if you know lambda, so if you know lambda, you know nu. If you know nu, you know lambda. Again, you'll see this equation again in Chem 1 if you have to take Chem 1. Alright, so just a little bit about waves, and you may have studied waves before in the past. If not, just know that waves have a wavelength and they have a frequency, and they are related through this equation. Alright, so continuous spectrum versus a line spectrum. So when we're talking about light traveling as waves, you may remember seeing a rainbow at some point. A rainbow has all the colors in the spectrum. It's a continuous spectrum. You don't see any sharp lines or breaks in between a rainbow. It's just one color kind of flows seamlessly into the next. There's no distinct lines. Nothing is interrupted. A line spectra, on the other hand, looks like something down here. So this is a line spectra where you can just see a few colors come out, and you don't see the entire spectrum. These individual lines are called discrete lines in this particular spectrum. And so what's happening here is kind of looks like the cover of a Pink Floyd album. But if you take like white light has all the colors in it, and you kind of shine it through this prism, you can separate all the colors of light, and you can see this rainbow spectrum. Now, if you do a similar experiment for like a metal, for an atom, an element, any particular element, and you try, you basically shine a bunch of light on it, and it's going to absorb some of it, but not all of it. Let's talk about why that is. But what you get out of it is just a couple lines. You get a line spectrum instead of the continuous spectrum. And this happens basically because of the electron configuration of the atom. So each atom has its own set of, it has its own number of electrons, and the way they're arranged is different from everybody else. And so you can get kind of like a fingerprint of each element based on its electron configuration, based on how the electrons are arranged. So this is what hydrogen looks like if you do this experiment. And again, all you're doing is you're kind of taking that element, giving it enough energy. It's going to absorb a certain amount of energy depending on what energy levels are available, where the electrons are, and or where they're allowed to be. And then when it releases that energy after it absorbs the energy, it can only release whatever it absorbed, and then you get to see this emission spectrum. So you can tell what kind of atom you have based on these particular spectra. So that's kind of neat. It's kind of like the fingerprint of each element. Okay, so energy released by the electrons is the form of massless packet called the photons. We talk about photons as the kind of the energy that's being released there, and based on the energy is proportional to the frequency, and frequency is proportional to wavelength, and wavelength represents different colors. So this is all kind of related. So this is related to any particular energy is going to have a different color. You can kind of relate it that way. And we're not really going to get into this too much, but light has both wave and particle-like properties. It's called the particle-wave duality. So sometimes it's easier to describe light as a wave, and other times it's easier to describe it as a particle. Again, we're not really going to get too far into that.